All right, what's up, AP Physics 1? Today we're going to be talking about applying our knowledge of circular motion onto problems. So, without further ado, let's get started. So we have a problem, and it states that a coin is placed 13 centimeters from the axis of a rotating turntable of variable speed. So this is a variable speed. It's not necessarily uniform circular motion anymore. The speed is varying. Okay, so a coin is 13.0 centimeters away from the center of a circle. Okay, and it is a varying speed. When the speed of the turntable is slowly increased, so it's rotating faster and faster, the speed is increasing. The coin remains fixed on the turntable until a rate of 38 revolutions per minute. So the table, increases in speed. When it reaches a speed of 38.0 RPMs, revolutions per minute, the coin on the table slides off. Ooh, that's not a good way to write it. The coin slides off. Okay? So they're asking us to calculate the coefficient, and I probably won't write the whole word. I don't want to write the whole word. I'll just say mu here because mu is the same thing as coefficient of friction. So calculate the coefficient of friction between the coin and the turntable. So calculate the coefficient of friction between the coin and the table. All right. So remember, rule number 1 of physics, always draw a diagram. So we have a turntable, and it is going in a circular motion. Now, the speed of the turntable is varying, but it's going in a circular motion nonetheless. So we will draw a circle to describe its motion, and there's a coin. We can draw a coin right here. Let's draw a coin. And it is 13 centimeters. So if the center of the turntable is here, the coin is 13 centimeters away from the center of the circle. Okay, so the table is increasing in speed, so there's not a defined tangential velocity. It's always increasing in speed in slow increments. But what we do know for a fact is that when the table reaches 38 revolutions per minute, the coin slides off. Okay, so we know that, in fact, when this tangential velocity is at its maximum, all right, the V tan max, if you will, of 38 RPMs, or 38.0 RPMs, excuse me. So when it's at its fastest speed, and I'm saying the fastest speed because that's the speed in which the coin slides off. So when its tangential velocity is at its maximum for when the coin slides off, that is the quantity that we'll be taking into respect. So even though the speed is changing continuously, they did give us a defined tangential velocity, a defined speed in which the coin will slide off. So we will take that value and we'll work with it. Now, it's asking us for coefficient of friction. Okay, so that means that there is a frictional force, meaning that we have to draw a free body diagram because there are forces acting on this coin. So we have to kind of take into account all these forces so that we can derive some equations. So let's kind of zoom in on this, and let's draw this coin. Let's draw the coin here. All right, it doesn't really matter where we draw the coin. We'll draw it here, whatever. And let's draw all the forces that are acting on this coin. So we know that there will be a gravitational force going into the turntable, all right, because this is a horizontal circular motion. So when the coin is resting on this turntable, it is actually applying a force on the turntable downwards. So this arrow is actually going into the turntable, and the turntable, conversely is adding a normal force, is applying a normal force on this coin. We also know that there is a frictional force that's going tangent to this circle. There is a frictional force. There's no applied force, but there is a frictional force. So maybe if I were to redraw this, because I'm kind of drawing it in terms of the turntable, if I were to say that this is the surface of the turntable, and I were to say that this is the coin that's resting on it. So let's say that this is a coin. All right. All the forces that are acting on this coin, we have a gravitational force, a normal force, and a frictional force. All right, so this is the surface of the turntable, and this is the coin actually lying on it. All right, so this would be our free body diagram. So remember, whenever we make a free body diagram, the most logical thing to do is to derive some equations. So we know that one equation we can derive is that Fn equals Fg. That's because the coin is actually lying, it's actually sitting on this turntable. If Fg was greater, then the coin would break the turntable and fall through. If Fn was greater, then the coin would be accelerating upwards. And since none of those things are happening, we know that Fn has to equal Fg. Now, we know that there is a frictional force. So we know that there is in fact, you can say there's a net force acting on this coin, but hey, remember if you watched my previous video, what is the same thing as the net force? If you answered it correctly, it is the centripetal force. So we can actually say that Fc, our centripetal force, is equal to, well, we have no force going in this direction, so 0, minus, well, we have a frictional force. So we could rewrite this as Fc equals negative, or the opposite of the frictional force. So let's use that as our backing. Remember, we want to calculate mu. We want to calculate the coefficient of friction. So Fc equals the opposite of Ff. All right, or the opposite of the frictional force. We know that Fc can be rewritten as the mass of this coin times v squared, the tangential velocity squared, over r, equals negative mu Fn. And we should know that Fn, that the frictional force is mu Fn from our dynamics, from our knowledge of dynamics. Does Fn equal anything? Can we rewrite Fn as anything else? Well, yeah, Fn equals Fg. Well, can we rewrite Fg as anything else? Well, yeah, Fg equals mg. So we could derive that Fn equals mg. So m times v squared over r equals the opposite of mu mg. All right, the opposite of mu mg. So now we can, if you saw the previous videos on how we dealt with problems like this, you know that we could factor out the mass on this side and factor out the mass on this side. And if you divided both sides by mass, you can cancel them out. So mass, we don't need mass to solve this problem. Mass is independent to this problem. So we could actually simplify this to v squared over r equals the opposite of the frictional coefficient times our gravitational acceleration. So now what do we have? We do have v squared. Our tangential velocity at its maximum, at the point where the coin slides off, is 38 RPMs. But once again, we don't really want to work with RPMs because we have meters per second squared on this side. That's our gravitational acceleration, and we don't really want to deal with that. So why don't we convert 38 RPMs to meters per second? So 38 revolutions per minute. And if we do a quick conversion, because we've done a lot of these conversions, we know that 1 minute is 60 seconds, and we know that 1 revolution will be the circumference of this. So that's just pi times its diameter. Pi times 0.16, remember, because you're doing, or 0.26, because 13 plus 13 is 26 centimeters, but we want it in meters, so we divide it by 100. So we have 0.26 pi. all right, 0.26 pi. If you multiply everything correctly, you should get 0.52 meters per second. All right, that should be its conversion. So 0.52 meters per second, we'll plug that in to our velocity, and we have to square it, because it's v squared, over our radius, which is 13 centimeters, but we want it in meters, because all our other units are in meters, so it's 0.13 meters, equals the opposite of our mu, times gravitational acceleration 9.80 meters per second squared. And if we multiplied both sides by 0.13, we would get 9.80 times 0.13, so 1.274. So we have negative mu times 1.274 equals 0.52. Well, we could actually do the math. So 0.52 squared equals 2704. I'm sorry. And divide both sides by 1.274 because we want to get mu all by itself. So the opposite of mu equals 1. Divided by this. Okay. So we get 0.21 for our frictional coefficient. Now you might say, oh, well, it has to be a negative number. Keep in mind that your frictional coefficient can never be a negative number. So this negative is really, it doesn't matter. You can convert it to a positive and you'll still get the correct answer. So in fact, so that basically means that negative mu should be the same thing as positive mu. Okay, so your mu equals 0.21. Well, in this case, your negative mu equals your positive mu. It's the same thing. So your mu, your frictional coefficient equals 0.21 for the answer. So that's your frictional coefficient between the coin and the turntable.